All right, so thank you very much, Brian, and thank you to the organizers of this workshop and all the people that have organized previous workshops like this in the past. They're always very fruitful, and I think this project is ultimately the result of one or many of those, so thank you. So this is joint work with let's see, Pedro and Alexandra and Junzo, who are all here now. So I guess what I want to tell you about is a sort of topological theorem about matrices. So look at the space of m by n real matrices, and and I'll think of it about as a Euclidean space, so an R to the nm. And then inside that, I want to think about the subspace of real m by n Toeplitz matrices. So Toeplitz means that the main diagonal entries are all constants. So you can have different entries in different diagonals, but along each diagonal, they're all the same. So that's Toeplitz. And I'll remind you what it means for a matrix to be totally positive if all the square minor determinants of the matrix are positive, and we'll say totally non-negative if all the determinants are non-negative. So our theorem is the following. Suppose you take the set of totally positive Toeplitz matrices inside this Euclidean space, and then take the closure of that set. So just meaning in the usual Euclidean sense, throw in all the limit points of those matrices. What do you get? Our theorem says that you get exactly the set of totally non-negative Toeplitz matrices. And I want to say that as plausible as this sounds, it's not quite as obvious as it might seem. Or if it is, maybe you can tell me, and that will change my whole life. So, so one thing I'll say here is that this equality, one containment here is easy. The set of non-negative Toeplitz matrices is obviously a closed set. It's defined by some linear equalities and some polynomial non-strict inequalities. And so it's closed. So it automatically contains the closure of this subset, the totally positive matrices. What's not clear is the reverse containment, which amounts to saying that every non-negative Toeplitz matrix is the limit of a sequence of positive Toeplitz matrices. And so the real question is, how can you cook up such a sequence for a given non-negative matrix? And if you just sit down and try to fuss with it and put parameters in your matrix, you see it's quite tricky because you have to make sure that you get all the minor determinants positive. So it's quite tricky. So before I talk about the proof, let me give some previously known results. The first one dates back to the 1950s. It's due to Anne Whitney, and she proved this equality for the set of arbitrary matrices. And again, the same problem as before, given a non-negative matrix, how can you find a sequence of positive matrices whose limit is that given one? And it turns out in this case, there's a very nice key lemma, which she proved, that says the following. Suppose A is a non-negative matrix, and suppose B is a totally positive matrix. Then the theorem is that if you multiply them, you get another totally positive matrix. And there's a small little caveat here, the asterisk. The A should have full rank, I guess. But the trick is, it's not super hard. It's just actually an application of Cauchy-Binet theorem. The determinant of the product is a product of the determinants of the minors of the factors. Of course, if the factors are all non-negative and positive, you can expect the total thing to be positive as well. But this is very nice because, again, as long as as long as A is full rank, now you don't need to find a new sequence for each non-negative matrix. You just need to find really one sequence of positive matrices that converges to the identity. And then you can just use that over and over to get a sequence of totally positive matrices converging to A. So it's a very cute trick. Unfortunately, it doesn't quite apply to the class of Toeplitz matrices because Toeplitz matrices are not closed under multiplication in this way. So, so we need to find our own little cute trick. Okay, so that's one thing. Very recently, Fallett, Johnson, and Sokol proved a similar result for the class of Hankel matrices. And Hankel matrices are very similar to Toeplitz. Hankel matrix means the entries are constant along the anti-diagonals. So in fact, a Hankel matrix is just a Toeplitz matrix turned upside down. And so again, Hankel matrices aren't closed under multiplication either. So they had to find their own key lemma. But the key lemma they found is quite striking. And I'm happy to share it with you here. It says that if you have a totally non-negative Hankel and a totally positive Hankel, first of all, Hankel, notice, just like Toeplitz, is closed under addition. It's a subspace. But the theorem is that if A is totally non-negative, B is totally positive, their sum is totally positive. Amazing fact. And it's not obvious. But I'll say that actually the fact here is really just a quick corollary of this lemma. Because, okay, I give you a non-negative matrix, pick your favorite positive matrix, and just scale it by a positive multiple and add it to A. And now you've got a sequence of totally positives that converge to your totally non-negative. So, easy. Again, unfortunately, this doesn't quite apply to Toeplitz because although Toeplitz is closed under addition, it doesn't preserve the positivity property. Somehow turning the matrix upside down messes with the determinants too much. So you need something else. So, whoops. So let me tell you about the Toeplitz key lemma. So first of all, let me say that it's okay if we assume that m is less than or equal to n. M is the number of rows. Because if I have a Toeplitz matrix, I can just take the transpose, and that's a Toeplitz matrix too. So might as well assume that m is less than or equal to n. And let me define these new parameters. Then what we can do is we can associate to every Toeplitz matrix a homogeneous polynomial in two variables of degree d, where d is the sum of m and n. And I'll do it in this way. So let me write f as a polynomial. Maybe I'll say it's normalized here because I've added the d choose k to the coefficients. And how do I turn this into a matrix? Well, what I do is I line the left and the top edge with the coefficients of f in this way. And then that completes to a unique Toeplitz matrix. I just complete along all the main diagonals. All the main diagonals hit the edge, so I get a Toeplitz matrix. And it's clear that this is an invertible process. You give me a Toeplitz matrix, I'll reconstruct the polynomial for you, and I'll just add the binomials and everything. In fact, it's actually linear as well. This is a subspace here, and this is a subspace, and the addition is component-wise in each situation, so it's a linear isomorphism of vector spaces. Okay. So our key lemma is this. The phi ID matrix of F is totally positive if and only if I is less than the Sperner number of A sub F, where A sub F is the algebra generated by F in the Macaulay dual sense, and that algebra satisfies the mixed Hodge-Riemann relations in degree I on the standard closed convex cone that I'll write as U bar. And you can identify this with the non-negative quadrant in R2 minus the origin. And the other part is a statement about totally non-negative if and only if AF satisfies mixed Hodge-Riemann in degree I on the standard open convex cone, which is the positive quadrant. So I just want to spend the rest of the talk, first of all, explaining what all these things mean. And then I want to show you how we can use this lemma to prove the theorem about Toeplitz matrices. So anyway, so that's the introduction, and please don't hesitate to stop me and ask questions if something is unclear. Sure. Yeah, sorry, it's a lot of writing here. So. Oh yeah, so I'm going to explain what all these things are. So S of F is the Sperner number of this algebra. So it's the maximum value of the Hilbert function. Yeah. So I'll explain everything, including what is exactly the algebra AF, what's the Sperner number, and what does it mean to have mixed Hodge-Riemann in degree I, and where does this closed cone come from? This closed cone really will live in the space of linear forms in A sub F. Please. It's not even closed in R2 because I'm removing the origin, but it's closed, but then I say again. Yeah, okay, yeah. So you have to remove the origin. Yeah, you don't want a zero linear form. Yeah, exactly. Is that okay? Yep. Oh, I see. Okay, sure. So so the question was what was the Sperner number, and this U bar is closed in the space of non-zero linear forms. Can't remember the rules. Okay. So let me explain here what everything is. So let's start with what I call oriented AG algebras. So an oriented Artinian-Gorenstein algebra of Sokal degree D over the real number field is a pair consisting of an algebra A and then what I'll call an orientation of A, which I'll denote as this integral operator. So the algebra is always going to be standard graded, finite dimensional as an R vector space, graded from degree 0 to degree D. I'll always assume the degree 0 piece is the ground field R. And then the orientation is this integral operator, and it's just a fancy name for a fixed choice of linear isomorphism from the top degree graded piece, which I'll call the Sokal, to the ground field. It's supposed to remind us of an orientation from topology where I integrate a volume form to get a real number, the top degree cohomology. And then the Gorenstein is a word that means multiplication in the ring gives us non-degenerate bilinear pairing between degree J and degree D minus J. And how does this work? I just multiply two forms of complementary degrees up to degree D, and then I integrate to get a real number, non-degenerate pairing. Maybe some people call it degree map. I call it orientation. Okay. But here's a fact is that oriented Artinian-Gorenstein algebras are uniquely determined by their Macaulay dual generators. And so what do I mean by this? So here's the quick setup. Take R to be the polynomial ring in n variables, and take Q to be another copy of the polynomial ring in n variables, but I'll distinguish them by using lowercase letters for R and uppercase letters for Q. And I want to declare that R acts on Q, or the lowercase letters act on the uppercase letters by partial differentiation. So you should think of maybe R as the polynomial ring of polynomial partial differential operators. And then if you give me a homogeneous polynomial in the capital letters of some degree D, I can look at the set of all partial differential operators that annihilate it. And that forms an ideal, and I can take the quotient and I get this algebra A sub F. And A sub F turns out to be an oriented Artinian-Gorenstein algebra of Sokal degree D, where D is the degree of the function F. Moreover, it even comes with its own integral operator, where, okay, what do I do with the degree D form? I treat it as a differential operator on a degree d polynomial, and I just apply it, and it gives me a real number. So it comes with a built-in orientation. And moreover, every oriented Artinian-Gorenstein arises this way. And I'll further say that two AG algebras are isomorphic as oriented AG algebras if and only if there's a linear change of coordinates relating the two. Okay, so, okay. And so these are the objects I'm going to be working with. These are my A sub f's. And now let me tell you what Hodge-Riemann is. So first, before I talk about mixed, let me talk about ordinary. So I have an oriented Artinian-Gorenstein algebra with some Macaulay dual generator. And let me fix a linear form in the ring. And let me fix some degree I between 0 and half the Sockle degree floor. So we can define the ith Lefschetz pairing. This is a pairing between the degree I piece and itself. And how does it work? I multiply two forms of degree I to get up to degree 2I, and then I apply multiplication by the linear form to the d minus 2I to get up to degree d. And then I apply that, I integrate, and I apply that differential form to f, and I get a real number. And so this is a symmetric bilinear pairing, may or may not be non-degenerate, depending on L is Lefschetz or not. Okay. And then I define the ith primitive subspace to be the kernel of multiplication by the linear form to the d minus 2I plus 1. And I'll explain this here with a picture in a minute, but with these definitions, I can say, what does it mean for the pair A and L to satisfy the Hodge-Riemann relations in degree I? And I'll abbreviate it with HRRI. It means that if I take the, for any degree up to I, of degree j, let's say, if I take the jth Lefschetz pairing, then that should be minus 1 to the j definite on the jth primitive space. And so that's what, so that amounts to really just a bunch of polynomial inequalities here. And I'll say Hodge-Riemann property if it satisfies the Hodge-Riemann relations up to the maximum possible, which is d over 2 floor. And I'll also use this language, weird. The HRRI on a subset of linear forms U means that AL satisfies HRRI for all linear forms in U. So here's a picture. This is the standard schematic diagram of the Hilbert function of some Artinian-Gorenstein algebra. And these colored boxes represent the primitive subspaces in each degree up to d over 2. And you can think of them, if you want, in terms of Jordan types. These are the beginnings of all the Jordan strings. That's what primitive spaces are. And the Hodge-Riemann says you should have this signature of the ith Lefschetz form on each primitive subspace, and it should be alternating by degree. And then once you know these signatures, you can fill in the rest of the signatures on the degree I piece using something called the primitive decomposition, which I'm not showing here, but just knowing the signature on the primitive allows you to fill in the signature on the whole degree I piece. And remember, I is just going up 0 to d over 2. So here's some example. So take take f to be x cubed plus y cubed. And then let's take this linear form, just a general linear form, c1x plus c2y. And then we can compute the primitive subspaces. I just need to go from 0 to 1. So that's d over 2 floor. And the primitive subspaces in this case are just each one-dimensional, spanned by these elements here. And then I can plug these into the Lefschetz forms in those degrees, and I get these polynomials right here. And Hodge-Riemann relations says that these should be positive. Or without the signs, I guess they should be alternating. But I put the signs in there. And so you can stare at these polynomial inequalities here, and you can see that the ring A satisfies Hodge-Riemann relations in degree 1, hence also Hodge-Riemann property on this set of linear forms U right here, defined by these polynomial inequalities. And I can draw a picture of U in the C1, C2 coordinate plane like this. Okay, so it's a union of two convex cones. Okay, so that's ordinary Hodge-Riemann. And now let me tell you what mixed Hodge-Riemann means. So mixed, instead of fixing a single linear form, I fix a sequence of linear forms, possibly different. They could be the same, but possibly different. And I could pick different linear forms for each degree. So maybe I should have written this as Li or something. And then I can define the ith mixed Lefschetz pairing. And so what I'm doing, it's the same as the Lefschetz pairing, except instead of multiplying by a power of a single linear form, I'm multiplying by the product of possibly different linear forms. Notice I'm holding off, I'm not including the 0th one here, but I include the 0th one for the primitive subspace. That's like multiplying by the L to the d minus 2i plus 1. So I have the mixed primitive subspace and the mixed Lefschetz pairing. And then when I talk about mixed Hodge-Riemann in degree I, I'll always talk about on a set of linear forms. So I say mixed Hodge-Riemann in degree I on U means for all degrees j up to I, and for all choices of linear forms in U to the d minus 2j plus 1, the jth mixed Lefschetz form for that choice should be minus 1 to the j definite on the jth primitive subspace for that choice. And we'll say mixed Hodge-Riemann property if it satisfies Hodge-Riemann in degree d over 2 floor, which is the maximum possible. So it's a little bit more complicated, and it's a little bit more general as well. Notice that if I just choose all my linear forms to be the same, this really becomes the ordinary Hodge-Riemann again. So here's this example revisited. So same polynomial, and now in each degree I can do a different choice of linear forms. So maybe I'll do some LIs with some C's, and this will be L0, L1, L2, L3. And I can compute the primitive subspace in degree 0, and that's actually always just 1. And then in degree 1, I can choose some different linear forms with some D's, and then I can compute the first mixed primitive subspace, and it's generated by this linear form here. So I can plug these into their respective Lefschetz forms, and I get these much longer polynomials here. Still cubic, by the way, or still same powers as the polynomials before, but just longer. And here, if you study these polynomial inequalities, the inequalities come from the Hodge-Riemann relations. These should both be positive. You can see, well, first of all, like I said, I could have chosen all the linear forms to be the same, and already that restricts me to my original set U. So I'm already restricted to this set U, but I further claim that there's a further restriction. So for example, I could choose L0, L1, L2 from one of these cones, but I claim that there's always a choice of an L3 in the other cone that will mess up one of these inequalities. So what I'm saying is you can't choose all your linear forms from both cones simultaneously. You have to pick one or the other. So let me just make this statement that it satisfies mixed Hodge-Riemann in degree 1 on this single cone. I could have chosen U2 as well, but I can't choose from both at the same time. So Yeah, because my inequalities would be violated. So you could imagine that if I chose if I had some C1, C2s, chosen from this one, and then I chose my C3s, down here, I could possibly make this inequality negative, and that would violate my rule. So I can't choose from both of those cones simultaneously. So I guess the message here is mixed Hodge-Riemann is stronger than ordinary Hodge-Riemann in this sense. And actually, we can make that a theorem. Mixed Hodge-Riemann on a set U always implies ordinary Hodge-Riemann on a set U. But the converse is not quite true. As we saw, we had ordinary Hodge-Riemann on the union of two cones, but we can't have mixed Hodge-Riemann there. You can also say that mixed Hodge-Riemann on U implies something I'll call mixed strong Lefschetz on U, meaning that instead of multiplying by L to the d minus 2i, you're multiplying by the product of linear forms. And that's giving you isomorphisms. And when I say SL in degree I, I'll always mean up to degree I instead of just in degree I. So, I think when some people say it, they mean the former, but I mean the latter. Why should we care about this? Well, I give some deeper reasons, I think, in the paper that we wrote. But the quick reason is that this property shows up in nature. If you have a compact Kähler manifold and you take A to be the cohomology ring with real coefficients in even degrees, and you take U to be the cone of Kähler forms in the degree 2 piece of the cohomology, then the statement is A satisfies the mixed Hodge-Riemann property on that cone. So it shows up in geometry, so maybe we should study it in algebra. And then, of course, this is the mysterious Catani theorem. So Catani shows in this paper in 2008 that if U is a convex cone and A satisfies the ordinary Hodge-Riemann relations up to the maximum degree, so Hodge-Riemann property, then that implies mixed Hodge-Riemann property on U. And so it's like you can get a converse of this fact up here under the right circumstances, which is sort of a mystery right now. And is there an elementary proof, or at least, can somebody, teach me the old one? Anyway, so what I want to do now is I want to get a concrete matrix verification for Hodge-Riemann. And we can do that with Hessians, or really what I'll call mixed Hessians. So mixed Hessians are a sort of generalization of the usual Hessian. And the generalization comes from what I'll call a polarization operator. So I think these polarization operators are used a lot in representation theory because it turns an arbitrary polynomial function into a more symmetric polynomial function, just in more variables. So in a fixed degree M, I'm taking a homogeneous polynomial in n variables of degree M to a homogeneous polynomial of degree M in nm variables. So it's like what I do is I stretch out each variable to a clump of m new variables. And then it's an R-linear map that's defined on polynomials. And what does it do? It takes a variable to a power and replaces it with the elementary symmetric function in that degree in that clump of variables. So x1 to the a1 goes to EA1, evaluated at the clump of variables x11 to x1m. And so monomials get replaced by these products of sums of square-free monomials in disjoint variables. And so monomials become these big giant sums of square-free monomials in many more variables. I think this sort of map maybe first appeared in Hermann Weil's book, but No. Sorry. It appeared in the 18th or the 19th century books first, maybe, but it also appeared in Hermann Weil's book. So, okay, and what am I going to do with this? Well, now let me go make like I'm going to compute the Hessian for f with respect to some homogeneous basis for the algebra A sub f, let's say in some fixed degree I. And the way that I compute the Hessian is I take pairs of basis elements and multiply them together in the ring, and then I treat them as differential operators and apply them to f. And this gives me a matrix whose pqth entry is this polynomial of degree d minus 2i in the n variables. To get the mixed Hessian, what I'm going to do is polarize those entries. And so now I get this matrix with pq entry, these big polynomials that are square-free in these mn variables here. That's my mixed Hessian. Is it okay? Please. Say again? Oh, thank you. Sorry. Yeah, I didn't even notice that. Yeah, the E stands for a basis in the second line, but in the first line it's elementary symmetrics. Yeah, so sorry. Is that okay? Is that okay? So we didn't just come up with this out of thin air. I mean, the fact is that if you take, let me call it C underline, by which I want to take, well, let's see, M here equals D minus 2i. So I want to take D minus 2i n tuples of real numbers. And I can use those real numbers to evaluate the polynomial entries in my mixed Hessian matrix. And so now when I do that, when I plug in, I'll get a real matrix, symmetric matrix, in fact. And my claim is that that real symmetric matrix is exactly equal to the matrix for the ith mixed Lefschetz map, where I'm using the linear forms that are parameterized by these weights. So these mixed Hessian matrices are exactly the mixed Lefschetz matrices for some choices of linear forms. And I can change the linear forms by changing where I evaluate the mixed Hessian. And so now we can use these to check the Hodge-Riemann or the mixed Hodge-Riemann. So A satisfies mixed Hodge-Riemann in degree I on U, if and only if for all j up to I and all choices of C underline and U to the D minus 2j, the mixed jth Hessian at C underline is non-singular, and its signature is this alternating sum of first differences of the Hilbert function up to degree, well, j. So, okay, it's complicated, but you can just check the signature of the mixed Hessian matrices and verify the mixed Hodge-Riemann. That's my point. Okay, so from now on, I want to, okay, oh, I guess I'm perfectly timed here. Okay, so now I want to focus on the two variable case because things get much simpler. And the biggest simplification that happens, let me just flash this up. So the Hilbert function of an algebra in two variables, but Artinian-Gorenstein algebra has a really nice form. It starts in degree 1 and increases by 1 in each degree up to a certain point that we call the Sperner number of A, or sometimes I'll call it the Sperner number of F. You can also think of this as the minimum generator degree of a generator of the annihilator. But the important thing here is that it increases by 1. And that means that the primitive subspaces in each degree should be either one-dimensional or zero-dimensional. In fact, they should be one-dimensional up to the Sperner number and then 0 after that. So Sperner number is a threshold. And the one-dimensionalness of the primitive subspaces means that to check the signature, we don't need to compute all the eigenvalues. we can just look at the determinants of the consecutive the Hessians. That's the statement. So for two variables, mixed Hodge-Riemann in degree I on U is equivalent to saying that the sign of the determinant of the mixed Hessians is this -1 to the j plus 1 over 2 floor. And here again, I don't need to go all the way up to I just need to check up to the Sperner number, or I, whichever's smaller. So anyway, so the Hessian determinant should have this weird alternating sign pattern, plus, minus, minus, plus, plus, minus, minus. That's what I'm looking for. Okay, so let me say, I mean now these are I'm going to bombard you with details here, but let me say that we can get quite explicit with these mixed Hessians in two variables. So suppose I have a polynomial written in its normal form like this, and let me fix an I less than the Sperner number, because that's all I really need to check. I don't need to go above the Sperner number. Well, since I is less than the Sperner number, the monomial basis is a perfectly good basis for my ring in degree I. And here's my first statement, is that the ith mixed Hessian is a Hankel matrix. It's Hankel. In fact, you can even show that in two variables, it has this really nice form. It's one of these, it's like a mixed polynomial with matrix coefficients. Hankel matrix coefficients formed by these normalized coefficients of your polynomial. That's why I normalized, by the way, so this would all work out. Look at these matrices. But okay, I don't want Hankel, I want Toeplitz, so I need to just flip the Hankel upside down. So what I should do is multiply by a permutation matrix. And let me take this one that just exchanges row P for row I minus P. That amounts to turning the matrix upside down. And now I can talk about the permuted mixed Hessian, and that turns it into a Toeplitz. Now, why would I want to do this? I mean, just in terms of Hodge-Riemann. Well, the point is that if you compute the determinant of the permutation matrix, it's exactly the Hodge-Riemann sign. And so now the mixed Hodge-Riemann, in terms of the permuted mixed Hessian, is a positivity condition. And so now we're interested in positive Toeplitz matrices, looking at the permuted Hessian matrices, permuted mixed Hessian matrices. Okay. And so now let's try to draw it all together in 3 minutes. So let me remind you of our linear isomorphism that associates a polynomial of degree D to some sort of Toeplitz matrix of dimensions I plus 1 and D minus I plus 1. I leave it as an exercise for you to verify that the rank of this Toeplitz matrix is exactly equal to the minimum of I plus 1 and the Sperner number of F. In fact, I think this is maybe it's a permutation of maybe what Tony would call a catalecticant matrix or something. And so let me just sweep a bunch of details under the rug and tell you the punchline, that the determinant of the permuted Hessian matrix can be computed as a linear combination of the determinants of the maximal minors of this Toeplitz matrix phi d. Moreover, the weights in that combination you can show are positive polynomials that evaluate positively on this standard open cone. And so now you can see how this works. If I assume that all these maximal minor matrices are positive, then these coefficients are positive, and that means the permuted mixed Hessians are positive, all on this open standard cone. And I can draw my conclusions from this here. So using this lemma and some other things that I'm not telling you, we can now obtain our key fact. So if phi d is totally positive, that means all of those maximal minor determinants are positive. It means all the determinants are positive, all the minor determinants. And you can show that that's equivalent to saying that those permuted mixed Hessian determinants are positive for all degrees up to I. And then you get this statement about mixed Hodge-Riemann on the standard closed cone and on the standard open cone. Oh, I'm at 40 already. Okay, sorry. Okay, just give me 2 minutes. So let me show you a quick corollary here that follows. So what I want to say is if I is less than the Sperner number minus 1, and AF satisfies mixed Hodge-Riemann on some closed cone, then okay, maybe F doesn't have a totally positive phi ID matrix, but I claim that there's some change of coordinates that does have a totally positive phi ID matrix. Here's an example. So here's AF that satisfies mixed Hodge-Riemann in this open cone. It's open, it's not closed. The phi I3 matrix here is this, and it's not totally non-negative. In fact, it's got a negative 2 by 2 minor. But you can do a trick. Let me take these linear forms inside the cone, and then I can take the closed cone spanned by those. Inside this cone, that means this algebra satisfies mixed Hodge-Riemann on the closed cone inside this. But then I could just change my variables according to, if I take x to L1 and y to L2, I could do the dual on the Macaulay dual generators and get a change of coordinates, turn F into G, and then AG will satisfy mixed Hodge-Riemann on the standard closed cone. And here's G, and you can check its phi13 is totally positive. So even though phi13 of F wasn't totally positive, you can make it totally positive because of mixed Hodge-Riemann. Here's a picture. So anyway, maybe I'm almost done. I've got one slide left. So here's the whole punchline. So how do we show this? I mean, let me take a totally non-negative Toeplitz, and I'll assume M is less than or equal to N, and let me assume that M has full rank. I'm not really allowed to assume that without loss of generality, but I can do it as part of a downward induction on rank. So this is my base case. Well, I know M is a phi ID matrix of some F in degree D, where D is M plus N, okay. Also, if M has full rank, that means that the I is less than the Sperner number. And also, non-negative means AF satisfies mixed Hodge-Riemann on the open cone. Okay, but then I could just perturb my variables a little bit by some little small t, and I get a linear change of coordinates. I could do my little trick, and I get a linear change of coordinates, a polynomial here that, well, has the same Sperner number as F, and it satisfies mixed Hodge-Riemann on the closed cone. And so look, the question is, I have a totally non-negative Toeplitz. How do I get a sequence of totally positive Toeplitz converging to it? Well, this is how. Now I could just take phi ID of GT. Here's MT, that's totally positive Toeplitz. And look, if I take T, if I take the limit as T goes to 0, GT goes to F. But phi ID it's linear, phi ID is linear, so it's continuous. So the limit of MT is equal to M, and M is in the closure. So it's kind of a weird little application of Hodge-Riemann to Toeplitz matrices. So anyway, there's a connection with Lorentzian polynomials. There's a connection with stable polynomials. I'll post my slides if you're interested in this stuff, but our paper's on the archive, and here's some other references. So thank you.